finally, the same thing we keep saying over and over. So what I've done, to be honest to those of you who will be experimentalists in future or who have to look at any data, also as a phenomenologist or theorist, I try to bring the main ideas of how to look at data. Now, I've asked my experimentalist friends to give me a list of things I'm supposed to teach you. And their list is at least 2 semesters long. If I had 2 semesters to teach you this course, I could teach you. But if you look at the list, I put some of the lists in this week's lecture notes. We're not doing so badly. We have covered like a half of the topics. And the main thing is that one has to learn about sum of squares. The key notion for all of this, for random walks, for diffusion, for all the Gaussians, Laplacians, flip coins, etc., is when you are fluctuating around something that on mean is 0, it's centered correctly, then every time you have to make an extra measurement and you produce an error in your measurement, the thing to always look is the sum of square. So it's the variance that's the main object. And I gave you some problem where you transport variances dynamically. Again, you have to sum them. So that's the main lesson of everything. It's called error propagation. And the main thing about error propagation is that if you're in higher dimensions and you don't have joint probability distribution, you can still compute the standard deviation of the variance by looking at errors and observing that the thing that's important is the correlation. And the main thing is, which I explained in this dynamical problem of having a distribution which is Gaussian being kicked by Gaussian noise at every unit in time. That's the same idea as here, is that the way that error adds up is that you have to add up squares of errors. In other words, you have to add up variances. If the things are uncorrelated, this correlation part will be 0 and you will be just adding them up. If they're correlated, you have to correct for it, and that's how they add up. So this is a 1-hour walk through a course which should take 2 semesters, and Ignacia Taboada will teach it while you're here as graduate students. I recommend it because he really cares about this stuff. About using, guess what? Linear methods to understand brains, to understand extragalactic neutrinos, to understand multi-messenger astronomy, where you compare the gravitational waves and neutrino measurements in the ice cube, and so many other things.
Can you just repeat the last 1 or 2 slides of the covariance?
I think I did it better in my notes. I'll repeat what I taught you before. These formulas, I'll just let you go through them by working your way through the PowerPoint slides. I just want to tell you what they mean. It has to do with Roger Penrose and Dirac. Penrose thinks in picture, Dirac thinks in formulas. The visual people hate formulas, but they do them because it's a language of, mathematics is a language of subject. But the meaning is not necessarily a formula. Let me give you the meaning of this covariances adding the way I understand it. And then you can kill me, but I don't want to write this formula because, it's totally straightforward. You understand what correlation is. I'll do it first by hand. Then I'll show you some pictures. So the idea is, suppose I prepare something in my experiment to best of my ability. So I'm in the basement of Hawaii and I prepare a beam of atomic particles, which are super cooled, and they're supposed to go into an experiment where I have a potential, which is a parabolic potential, and they'll do something. So, I prepare them. And the best I can do is a Gaussian distribution of them. It's very hard to prepare something that's sharper. It's the minimal information distribution that you have. So I prepare them in such a way that, their height is pretty good, but their velocities are distributed. So I have a covariance matrix that describes a cigar of them in a phase space, in which maybe positions are reasonably sharp, so they're narrow in some directions, but they're wide in other directions. So, it's almost impossible to prepare something that's a perfectly spherical distribution in phase space, when you're mixing up velocity and positions. So that's the initial distribution. And now it's moving in a world where there are two things. One is there is some law. So, for example, it's falling down in a combination of electric and magnetic field. So it moves on some curved trajectory. Each particle doesn't care much about its neighbors, but they're neutral particles, but they do follow the law. So, they follow this way, number one. Number two, they're in slightly noisy fields, so let's see. The Bluetooth on your phone is in the room, shouldn't be there, but you brought it in, and it's disturbing your measurement. So, there's some noise going on. So noise, again, is another cigar, because noise might be in wrong direction, but weak in magnetic direction or something, depending on what it is. So what's happening is you have a covariance that describes your initial particle. It's being transported, and then you kick it by noise. And that means you're kicking it by a different cigar. And now the question is, what's the result? Now there's this amazing thing, which is called convolution of two Gaussians. It turns out that if I have two Gaussians, I convolve them. The resulting variance matrix is a sum of the two covariance matrices. You did it as various exercises. So it turns out that the result is a cigar, and it's a non-obvious cigar because, I had errors coming from my knowledge of my distributions, and I had errors coming from the external world, the noise. But the result was a cigar, which is, whose covariance I know. And the most amazing thing about a cigar is these covariances just add up linearly. That symmetric matrices add up. Two of these stupid symmetric matrices, I get something else. And that's actually correcting for the Gaussian. So that's, the meaning of covariance is that. I am in zillion dimensions, of which I can only draw one. And I prepare, to best of my ability, a particle. Classical here, but quantum doesn't, it's pretty similar, the quantum situation. Put it where I want to put it. But being a mere human, what I actually prepare, when I do this experiment 1,000 times, I prepare a cigar of particles that are concentrated in this cloud. And this cigar is, one standard deviation surface of the probability distribution of, in 1071 dimensions. But that's what I prepare. Then I say, according to the holographic principle, blah, 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 there is an equation that says when I integrate it time t later, so this is my x, I end up here. Every point follows it, also the mean of the distribution, the center follows it. And what I get is a new distribution. Well, maybe I should call it brown, which has been deformed by the flow because neighboring trajectories have slightly different behavior. But in the approximation that we look at a tangent-space linear neighborhood, this is produced by a matrix, and this matrix called Jacobian has its eigendirection, eigenvalues, which enable me to compute the new distribution. And the main trick is that if this one was described by covariance matrix Qj, the new covariance matrix is Qm M transpose. Sorry. So Q at time t is Jacobian acting on one of the axes, delta axis in linear approximation. And covariance matrix has X and X transpose. It's sandwiched between two of them, so Jacobian appears twice. It's computed on this evolution, and that's what deterministically happens to the neighborhood of a trajectory. Cigar just gets deformed into different cigar. Then I kick it, and the kick is a totally different distribution, which I call, whose variance is, I call it delta, let's say. And that's something that's, either smaller or bigger. Hopefully it's much smaller than my preparation. So for a short time, I don't destroy my particle by noise because, I give it relatively weak kicks. It's only at long time I have to worry. So there is a new ellipsoid. And that one depends on where I am in the space. Or might be, in an ideal approximation is it doesn't matter where I am. My Bluetooth is the same wiggle any place in this experiment, but it could depend or not depend on X. So that's ellipsoid. So now this kick is called noise, and it's assumed to be white noise, meaning it's uncorrelated. Next time I kick, I will not remember how I kicked it before. So that's a crucial assumption. And now I find that Q, the new distribution, its covariance, so this is a matrix at time, after n kicks, is the previous covariance I had transported and deformed by deterministic flow plus the noise. Well, it's just a matrix, so I don't have to put the synthesis. So yeah, that's pretty amazing. So this is called covariance evolution. So the way it works is that, there's a correlated part of it because deterministic laws are absolutely correlated. I have absolutely correct result afterwards. So this is correlated part by, let's say by Maxwell or somebody. And this one is the extra noise, which we cannot control. Whatever is producing the noise in the system. The main thing is that this measures squares, because this is measuring expectation value of x time x transpose. And it has two components. This particular sum of squares came from our preparation. So it's systematic, if you wish, error or whatever. It's system part. And then there is real noise, but they simply add up. So quadratic errors written in quadratic errors, correct ways to write them as covariances, add up to give me a succession of ellipsoid that I see. This is exact for a situation where I have Gaussian distribution prepared and I have noise which can be approximated by Gaussian. And if the laws are not quite linear, so this is only correct for, well-prepared distributions and weak noises. If noises are not linear, then I have to look at next to leading terms, and that's called quantum field theory, quantum electrodynamics, Young-Mills, celestial mechanics, the extra stuff that has to be put in. But the leading behavior is always sum of squares. That's what experimentalists call error propagation, and write some formulas. For me, it's easier to draw them for you. And, depending on how you comprehend stuff, you can ignore me or you can say, oh, that's what it means. Both ways are totally legitimate ways of human understanding.